All, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to basically discuss restoring division algorithm and non-restoring division algorithm, which are basically used for performing division. Now let us see how we are going to perform this restoring division algorithm with an example. So let's say if I am going to divide 14 and 3, right? Now this particular algorithm is going to deal in the binary format. It is going to basically help us to perform binary division between the numbers. Now, this 14 is nothing but 1110 and 3 is nothing but 0011. This is nothing but my dividend. I'm representing my dividend with a small letter A and my divisor with a with capital letter M. This is nothing but my notations. And quotient is basically represented with Q. This is nothing but my quotient. Now, for representing my dividend, I have four number of bits. So over here, n is nothing but number of bits to represent your dividend, which is nothing but 4. Okay. Now, I'm also going to use something known as accumulator. So this accumulator is used to store your temporary results. That means your partial reminders. And this is initialized to zeros. And the width of this accumulator is n plus 1 bits width. N plus 1 bits width, which is nothing but 5 number of bits. Okay. Now, and we are going to basically follow this particular process for until and unless this n is equal to 0. So for every process we are going to decrement our n. That means we are going to follow this process for 5 number of times. Now let's say we are in step number 1. Let's see the step number 1. So in the step number 1, I'm going to initialize my accumulator. Accumulator will be 1 2 3 4 5 zeros. Okay. Next is my quotient. So basically quotient is loaded with your dividend value initially. So quotient is basically loaded with dividend value. What is the dividend value? 1110. 1, 1, 1, 0. This is nothing but your quotient value. And our divisor m is equal to 0, 0, 1, 1. These are the initial values which I'm going to have. Now I'm going to left shift my accumulator as well as quotient. So whatever the content which is present inside your quotient, that will be left shifted into your accumulator. And the accumulator value will be equal to 0, 0, 0, 0, 1. That means it is left shifted towards here. And the quotient value will be equal to 1, 1, and 0 and 0. This is my quotient value which I'm going to have. And my dividend value is, that is my divisor value, is nothing but same. Here I have performed left shifting operation of my A and Q. Next I'm going to subtract A with A minus M. Now instead of performing A minus M, I can basically perform A plus 2's complement of M. Now what is 2's complement of M? So 2's complement of M is nothing but, let me write down over here. So 2's complement of M is nothing but 0011, right? So 0011, it is nothing but 1, 0, 1 and 1, which is nothing but 1101. So instead of subtracting it, I can basically add 0, 0, 0, 0, 1 with 2's complement of M. I'm going to take total 5 bits, which is nothing but 31101. 11101. Now, if I'm going to add this, I'm going to get 1101, 1, 1, 1, and 1. You can see this is the final value if I'm going to perform A is equal to A minus M, that is being stored inside your accumulator. Now, accumulated value here is 1, 1, 1, 1, 0. Now you can see over here, accumulator's MSB is basically equal to 1. That means whatever the result which I have got is a negative result. Now if I'm going to get a negative result, what is that I should do is the quotient register should be, the quotient register's LSB should be filled with 0. Okay, so if I'm going to get my MSB of your accumulator is equal to 1, Q of 0 should be equal to 0, and we should basically restore our A. So what do I mean by this? So what I'm going to do is quotient is basically 1, 1, 0, and the LSB is filled with 0. Okay. And accumulator should be restored. Now what do I mean by accumulator restoring? I'm going to add our accumulator with my divisor value, which is 0011. So 0, 0, 0, 1 and 1. So what is that our result is? So it is 1, 110 is 1, 110 is 1, 110 is 1, 110 is 1. We can discard this carry. So we have basically restored our accumulated value to its original form. Now accumulated value will be updated to 0, 0, 0, 0, 1, and the quotient value is 1100. So this is the final accumulator and quotient values after performing step number 1. Okay, so I'm repeating myself again. In the step number 1, if your accumulator after subtracting a is equal to a minus m, if your accumulator's most significant bit is equal to 1, you should make your LSB of your quotient is equal to 0, and you should add your accumulator with your m. Okay, not with the 2's complement of m. You should add with the original m value, a plus m. Okay, this is a minus m. You should not add with the 2's complement of m. Okay, now let's move to the step number 2. So in the step number 2, we have the accumulator value to be 1, 2, 3, 4, 1, and the quotient value is basically 1, 1, 0, 0. Okay, and m value here it is 0, 0, 1, 1, and 2's complement of m is basically 1, 1, 1, 0, 1. This is nothing but my 2's complement of m. Okay, yeah, that is 31101. Now again, I'm going to perform this shift left operation in the step number 2. So what is that we are going to get? So E value will be updated to 0, 0, 0, 1, and this one will be shifted over here, 1. And the quotient value is nothing but 1, 0, 0, 0, 1, 0, 0. Okay. And now after performing left shift operation, this is nothing but my left shift operation which I have performed. After performing left shift, what should I do? I should basically subtract a with m. So what is that we are going to do? If I want to subtract a minus m, then I can perform a plus 2's complement of m. Okay. So that is what I'm going to do. A is nothing but 0, 0, 0, 1, 1 plus 1101, 1, 1, 1, 0, 1, which is 1101, 1101, 1101, 1101, 1101. So this is my accumulated value. And over here, you can see you are going to get a particular carry. Okay, so you are going to get a carry that you can discard basically. That means this is your final result, which is basically a positive result which you have got. Okay, since you have got a positive result, what is that? That means you can basically restore. If you can see most significant bit of your a is equal to 0, that means you can make your quotient LSB to 1. Okay, so quotient LSBs can be made to 1. So what do I mean by this? Now accumulated value will be 0, 0, 0, 0, 0, and quotient value will be equal to 1, 0, 0, 1. So quotient's LSB can be made to 1. Okay, and here m is equal to again 0, 0, 1. This is the end of the step 2. So by completing this step 2, our accumulated value is all zeros, quotient value is 1001, and m is equal to 0000. Now in the step 3, let's see the step 3. So in the step 3, we have the accumulated value to be 00000, and my quotient value is basically 1001, and my m is equal to 0011, 0011, and 2's complement of m is basically 11101. This is my 2's complement of m. Now again, perform the left shifting operation. So what is that we are going to get if we are going to perform left shifting operation? It is nothing but 0000, and this will be shifted over here 1. Okay, and quotient will be equal to 0, 0, 1, 0. This is my quotient value. Now I'm going to perform A with my M. I'm going to perform A plus 2's complement of M, that is nothing but A minus M, which is nothing but 0, 0, 0, 0, 1 plus 1101, 1, 1, 1, 0, 1. So what is that I'm going to get? 110 is 1, 1, 1, 1, 1. And you can see MSB of your accumulator is equal to 1. That means it is a negative value. If you are going to get a negative value inside your accumulator, you should make your LSB bit of your quotient is equal to 0. So that means Q is equal to 0010 only. Okay. and you're going to add this accumulator content with this m. Okay, not with this. If you're adding this with this, you're performing a minus m. You should perform a plus m because your accumulator's MSB is equal to 1. So what is that we are going to get? 4 ones 0 plus 0 0 0 1 1. So what is our answer? It is equal to 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 0 1. If we are going to get any carry, that we are going to discard, and this is the final result of our accumulator, that we are going to have it as 0 0 0 0 1. This is my final result of my accumulator after performing step number 3. Okay, now let's perform step number 4 and let's see what is that we are going to get. So in the step number 4, again, I'm going to basically perform left shifting. I know the accumulated values triple four zeros once. Now, after performing left shifting, it is nothing but accumulator is equal to 1, 2, 3, 1, 0, and quotient value will be equal to 0, 1, 0, 0. This is my quotient value. Now what is that I can do over here? So I'm going to basically subtract this a and m, that is nothing but a plus 2's complement of m, which is 0 0 0 1 0 plus 1 1 1 0 1, which is 1 1 1 1 1. So again I'm getting this particular value which is again negative. So what is that I can do? I can basically, perform q of 0 will be equal to 0 and your a value will be restored. So that means a value will be restored. That means you are going to add this with this so that you are going to get again triple 0 1 0, and your quotient will be equal to 0 1 0 0. This is what you're going to get. And over here we can see in the step number 4, our accumulated value is 0 0 0 1 0, and our quotient value is nothing but 4. So what is this? This is nothing but my final remainder, and this is nothing but my quotient value. So if I'm going to divide 14 with 3, 3 times 4 is 12, and my remainder will be equal to 2. This is what my result is. Yes. So this is how we are going to basically perform restoring division algorithm, where if your accumulator is negative, you are going to restore the previous value, but if your accumulated value is positive, you are going to continue with that particular value itself. Yes. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.